Last time we had talked about this idea of what we call the pumping lemma. I gave you some intuition behind it, and I wanted to formalize it now with you. So we're going to be proving now the pumping lemma. So I just wanted to restate the pumping lemma first and give you a quick intuition or recap from last time, and then we're going to prove this sucker. So let L be a regular language. There exists a constant p, and remember we said that this is also known as the pumping length, and it depends on the language. So when we think about this constant p, we're going to have some way when we prove the claim how we can determine what that p is. Such that for all strings in the language, with the length being at least the pumping length, you can take the string w. It's going to be able to be broken into these three parts where it has these three properties. First, the y part is non-empty, meaning that it consists of at least one symbol. This y part happens near the beginning of the string, namely that xy of the first two parts of this three-part decomposition or dissection of the string into three substrings. The first part and the second part cannot be any longer than the pumping length. And the third property is that for every k greater or equal to 0, I can tell you that the string xy to the k z is in the language L. And we call this the pumping lemma because I get the opportunity to pump y. What does that mean? It means that for any string w, where the length is at least the pumping length, there's always going to be a non-empty string y near the beginning that can be pumped, and that means that I can take y, I can repeat it 0 or more times. That's what I refer to as pumping. We're pumping that string. So each one of those, for different k's there, for example, xz would be in that language, xyz is in the language, xyyz is in the language, xyyyz is in the language, and so on for that third property. So we're going to be proving the pumping lemma next. So when I first introduced the pumping lemma to you, I gave you some intuition behind the underlying mathematical machinations of this thing. And there's the dreaded M word again, but it's rather important here. So we're going to prove this claim now. So suppose L is regular. What does that mean by definition? At least how we define the regular languages. It means there exists a DFA, right? There exists a DFA. So then, by definition, there is a DFA, M. I'm going to call it M. M for machine. Where L of M, so the language of this machine is equal to L. Now, suppose, so this is where that P part's the pumping length's gonna come up, and this will remind you of the example we did earlier. Suppose M has P states. This should just make your ears ring a little bit if you've seen our example where we constructed such a DFA that meets some of the conditions we had over here. So I must stress that you can't always do that, but the point is that in that example I tried to highlight some elements of the pumping lemma. Suppose M has P states, and let the transition function, delta, so I'll let delta be the transition function of M, and Q0 be the start state. So now we're going to consider a string y. So an arbitrary string. We're not going to do y. I was about to say y. I meant w. W, which meets the conditions of this theorem, where the length of y is at least the pumping length. Which, remember now, the pumping length is the number of states of this DFA. Akin to our example we had seen. Such that W is equal to A1, A2, and so on, AM. So it's going to be equal to this string. So it's going to go A1, A2, A3, A4, all the way up to AM, one after the other, with M being at least P, and every AI is an input symbol. Now, you might ask, Dan, what are we going to do now? Because I don't know what the DFA actually looks like, right? This is a complete, like, I don't know what the DFA is, right? I just know it exists. Because that's what I got for free when it was regular, right? I brought into existence a DFA. I don't know what the DFA looks like. So here's the technique we're going to use. Is we're going to take and we're going to imagine we're going to lay on top of the DFA labels that are going to represent the states that are in the DFA based on the transitions that it takes with W. So it's like we're going to take our DFA and imagine I go there with some tape. So I'm going to go over there and I'm going to give names to those states. And I'm going to go over there and just like, okay, even if the DFA had different names for these things, I'm going to give them labels that are going to make it easier for us to do it. So for example, if the state is literally called like Q1 or Q2 or something, I'm going to call it like P something. So I'm going to like put the piece of tape on there and I'll say, this is what that state is. So I can give it names, because remember, I don't know what these look like in the remember, this has to work regardless of what the DFA looks like, right? So I'm going to give names to these states. And remember, I'm going to consider an arbitrary string, and these labels are going to represent and be assigned per W. So you'll see what I mean in a moment. For each I is equal to 0, 1, 2, all the way up to P. So I'm going to give labels to these states now, as I talked about. Just imagine I'm taking out the tape. I'm going to put them on top of the states. So imagine I draw out the transition diagram. I'm just going to put tape on those ones, and I'm going to give them names as per the execution of the DFA with respect to W. Because remember, I can always label them per W each time, right? I can consider any one like this, and I can just label them. And the natural thing is going to come back to thinking about it just like a walk or path of the execution of the DFA. And those labels are going to be how it's going to play out. So I'm going to put labels. Imagine I'm just taking that big roll of tape and I'm just going to take out pieces. I'm going to label parts of the states. Because remember, I don't know what they are, but I most certainly know, based on its existence, how it's going to operate. But I have names for these things, right? I don't know for a fixed one what it's going to do until I see it, right? But I know that it does indeed compute just like any other DFA. So we're going to define PI, so that's what the name of our states are going to be. It's going to be P0, P1, P2, all the way up to P. I know I had a little bit of fun with that one. to be whatever the result of the extended transition function from Q0 upon reading A1, A2, all the way up to AI. i.e., PI is the state M is in after reading the first I symbols. of W, where I'm going to just simply define that P0 is equal to Q0. Because when I haven't read any symbols, right, where does that take me? Well, by the definition of this, if I haven't read any symbols yet, you'd agree with me that I'm just staying at the start state, right? So this is how I'm going to define each one of my labels for the states. So these are going to be states that are going to be describing what we had seen before when we went for a little walk in the DFA. So that's what P0, P1, P2, all this are. I must stress for those that are quite literally looking at this and be like, okay, well, you have a P here and you have a P here. Remember, this was describing a state with a subscript. This P here is meant to be a number. So I must stress for those that are quite literally looking at this and be like, Dan, you used P twice. Just think of this as a stylized P, like this is a special label, okay? A special number, a constant, a pumping length. We have how many states now? Well, I want to remind you what this all looks like, right? So it's going to look something like this, right? Let me just draw it over here because we're going to use this to help us with our intuition here. And this will remind you a little bit of something we've seen before. So I have P0. So that's, remember, that's where we start the DFA. Its execution's at. And you would have P1, P2, and so on. Stuff will happen here. Stuff happens in here. And then eventually I get to some state Pi. And maybe some other stuff happens. And then I go from there to the final state. So please note how many states I have just labeled here. How many are there? How many are there? Are there P that I've labeled, or is it P plus 1? Take note of the indexing I used here. So how many distinct states are there? Well, let's think about it now. This is the conundrum, right? How many are there? Well, that's what you would think, right? But this is the catch, is remember, how many states does the DFA actually have? It's P, right? So here we go. This is what we'd seen previously when we thought about this. So check this out. So notice that so even though I've listed out P plus 1, right? There's P plus 1, right? But the thing is, there's only P states, right? Notice there cannot be P plus 1 distinct states. Distinct states. Distinct states or distinct states P, or I'll say distinct PIs to make this even more fun. There cannot be P plus 1 distinct PIs, as there are only P states, namely the pumping length states, right? There's only that many. Now, people ask Dan, why is it so important that I have some knowledge of this whole discrete M word thing, the mayonnaise, the mustard? Because when you stare at something like this, when I have a collection of things and I want to ask, can I categorize all those things with respect to the number of things I have? What I just said to you is that you can't take each one of these and put them into the same buckets as the number of states, right? There's going to be one extra. There's a lovely theorem that we had talked about before when we've explored discrete mathematics. It starts with a P as well. It seems like today is just full of P. Let's see here. what was it called? This thing where I put like cats in boxes and things like that. And if I don't have enough boxes for each one of the cats, I had to put at least 2 cats in the same box. Well, it was this thing called the pigeonhole principle. This is actually one of those classic places where you would use the pigeonhole principle in computer science. But it appears all sorts of places, but this is one that a lot of people will point at and say, this is why you should be aware of the pigeonhole principle. That is, I was going to say there is, that is, by the pigeonhole principle, there exists 2 integers, I and j, because you remember, think about these as if I uniquely numbered the states. Kind of like over here, right? 2 integers, I and j, so that we're going to have it so I and j are sandwiched between 0 and the pumping length. And states pi is going to be equal to pj. So somewhere in between 0 and p, right, because of the way we defined each of these pi's, they're going to be along the walk that we take to get to the final state, right? Just like we have here. What I'm saying is that because of the pigeonhole principle, there's going to be 2 indices, 2 integers, I and j, such that this I is going to be equal, like pi is going to be equal to pj. So it means that even though it can happen later on, it's going to happen such that it's going to be, or pi is going to be equal to pj. So when I come around with my stickers, when I labeled p, like pi and pj, they're going to land on the same state. Is that clear, everybody? Then we can divide w into the 3 parts, x, y, and z. Because remember, w is in the language, right? So please remember that. It's a very important element of this. Otherwise, you couldn't guarantee that when you execute the DFA that you get to a final state. So remember, I'm just labeling some of the states that are taking me to that final state. So let me just take that picture again, and I'm just going to draw it again up here to help us see what's going on here. So I had P0, I have Pi, and I have some final state. And that takes me, so I do some stuff after I approach P0, some stuff happens, and then I get over here, right? So what can we say here? Well, let me write out what x, y, and z might be. So let's check this out. So x is A1, A2, all the way up to AI. So that means that x makes us reach state Pi. And I must stress that x might be empty. There's nothing stopping x from being empty. You could just get straight to Pi right away. So that's what x is. So x is going to be here, right? So x is A1, A2, all the way up to AI. All of the transitions, so this would be like the part of the pathway that I take and I follow with my finger that gets me right here. Next, based on what we discussed previously, I get AI plus 1, AI plus 2, all the way up to AJ, right? And we established that when I get to reading AJ, where does that put me? That puts me back at PI, right? Because PI is equal to PJ. So take note of the subscripts here. So y takes us back to PI, which is equal to PJ. But remember, y is not empty. That's the thing you really need to notice, right? It's not empty. I want you to think about why it's not empty. So remember, x can be empty, but y can't be empty. Well, remember what we said about the pigeon principle. Remember, we get two integers such that they're sandwiched in between here, but they're two distinct numbers, right? So that's what y is. So y is right here. So if I were to follow my finger around, it would get me back here after the DFA has read this. Then the third part. Z is AJ plus 1, AJ plus 2, all the way up to AM. So this is just simply the rest of W. Again, Z may be empty. Now I've shown you how you can decompose or dissect, whatever fun word you'd like to use for today. I showed you how you could dissect the string into 3 parts. Now I got to show you the third property, right? Because remember, we established that y is not empty, right? What are the things that we have to establish? That xy is at least the pumping length, right? But what do we know? Most certainly, notice that j is at least the pumping length. But that's the end of y, right? That's the end of y. So that means that we've satisfied the second condition. The third condition, this is the one that's I would argue is the most interesting part about this, is the one that allows us to discover more strings that are accepted by the language by pumping y. So this is the last part of the proof. Consider when M processes string x, y to the k, z for any k greater or equal to 0. Let's break it into 2 cases. First, we're going to look at when k is equal to 0, what happens with the DFA, and we're going to look at what happens when k is greater than 0. So we're going to break it into cases. So if k is equal to 0, then what happens? Then M receives input xz. And what does it do? What does it do? Let's follow with our finger, okay? So if I give you xz, what does it do? It goes boop. It follows all the way along, gets over to pi, and since there's no y part, right? It goes all the way to the final state. And that's what's going to happen when k is equal to 0, right? And goes from p0 is equal to q0 to stage pi on x. Since pi is equal to pj, M then goes from state pi to a final state on input z. So that means that M accepts xz. But what does that mean? It means it's a part of the language, right? So that's the first possibility. There's another possibility, right? So let's consider the other possibility right here. Is otherwise k is greater or equal to 0. And then m transitions from q0 equals p0. Or is it p1? Transitions from here to pi, right? On x. That's what it does, remember? It goes from here, follow along the transitions to get me here. Then what does it do? What's it do? How many times does it repeat? Follow along this. How many times does it do it then? It's going to use that y part. How many times? I'll start writing and you tell me, okay? Then goes from pi to pi. Exactly how many times? Because remember, the string has this form, right? So k is now greater than 0, so it's going to take this alternative route. But the thing is, the route depends on k, right? So how many times is it going to repeat y? Namely, what is the DFA going to transition on? So it's how many times is it going to go from pi to pi? So there's going to be potentially some other states that happen in between here because pi is equal to pj, right? But how many times does it happen? It happens k times, exactly k times. So it does it exactly k times on input y to the k. And then goes to the accepting state. The accepting state on input z. Accepting our string, right? Accepting x, y to the k, z. Now that we've considered all possibilities that can happen with k, now we can summarize the last condition and we've established the truth of the claim. So for any k greater or equal to 0, sorry, I'm getting really excited here. X, y to the k, z is also accepted by m, implying that x, y to the k, z is in the language L. And that completes the proof. So that concludes the proof for the pumping lemma. So remember, we satisfied the 3 properties for how we can dissect W. So it's x, y, and z. And remember, the point here is that W has at least the pumping length, which in our proof is the number of states of the DFA. And the whole trick here that we had was that we gave labels to the states for which W would execute. And then we noticed that, akin to what we previously discussed, that there's not going to be enough states for me to describe them all as distinct. There's going to be a repeat that happens. And we just gave names to those, and then we were able to characterize what the path or walk that the DFA takes when it's executing string W.